Mrs. Sindhu pursued her bachelor's degree in information technology from Havinashalingam University, Coimbatore, and did her Masters of Engineering in CSE from Velamal Engineering College, Chennai. She also completed her MBA with specialization in human resource and marketing in 2016 from SRM University, Chennai. She has published several papers in Scopus and SCI Index journals and has presented in reputed international conferences within her 8 years of experience. Her current areas of research include sentiment analysis, recommendation system, text processing, and affective computing. She is a member in professional bodies like Institution of Engineering and Technology IET and Indian Science Congress Association ISCA. She has organized various events like international conferences and national workshops. Mrs. Sindhu has made remarkable achievements and won awards, including a Top Performer Award in the Faculty Development Workshop on Red Hat OpenStack Cloud. With all that being said, I would now like Mrs. Sindhu ma'am to take over the session and enlighten us with her insightful thoughts. We would really love to hear from you, ma'am. Over to you, ma'am.
Thank you, Sangeet Sahana, for those kind words, and thank you for that introduction. So directly I'll jump to the topic, and I thank everyone for having me here. So let me present my screen. Do let me know if it is visible. So is my screen visible? Am I audible properly?
Yes, ma'am.
Okay. So today's topic that I'll be discussing for an hour or so is on design and analysis of algorithms. So this is a very elaborate topic, but given the short period of time that we have here to discuss, so I've made all the key points that is essential for a second year student to know why this subject is important or why this topic is very, very significant to a computer science engineer. So design and analysis of algorithms. So today's agenda will be on why should we go for this design and analysis of algorithm, what it is, what are the strategies which are required or which you should know for analyzing and designing algorithms, and how do we do it. So the first topic is why should we go for this topic, design and analysis of algorithms. So the answer is to solve any problem. So be it any problem, and if I'm not audible somewhere, please do let me know. So be it any problem that you come across in everyday life, what we need is a solution, right? So as a computer science engineer, what we do is before we write a program, we go for putting it in some form. So the solution for a problem can be plotted in a diagrammatic representation, be it a flowchart, or sequence steps of instructions, be it algorithm, or pseudocode, which is in between an algorithm and a programming code. So having said that, you have a problem, you have some ideas for the solution, right? You plot it in one of these, and then you go for making it into a program. And after you do the program in any language that you know, C, C++, or Java, or whatever it is, then you get a solution. So if this is the process, then what is the need for this design and analysis of algorithm? So the point is, we don't have a single solution, right? Any problem you have, then you get to have n number of solutions to that problem. So that is where we go in for this design and analysis of algorithm. Which solution should I choose? So depending on various criteria, the given scenario, we can pick one solution, right? So that is why we are going for this design and analysis of algorithm. So you have the problem to be solved, right? The most convenient way of putting it in before you go in for creating the program is an algorithm, right? If it is a very big problem, you cannot go around drawing diagrams and all that, but this is very convenient. You can write an algorithm, right? And then you convert it into a piece of code and you feed it into the computer. Obviously, any problem should have a set of input, okay? And when you're feeding it into the computer, you get the output. Now, this output can be either correct or it can have an error, right? So these are the scenarios when you're creating algorithms. So as such, what is an algorithm? So the default definition is it is a sequence, a set of unambiguous instructions, right? And these are the characteristics of algorithms. You should have specific sequence. Okay, first this instruction, then this instruction, and so on. Then it should have some kind of computation. Only then it can process and give you an output. And any algorithm should have input, it should have output, and it should have a finite time within which this algorithm can process. It cannot go on in an infinite loop with never-ending process, right? And all the instructions that we give should be unambiguous. So these are the characteristics of an algorithm, right? Now, first of all, design and analysis of algorithm is whenever you have any problem that you face in day-to-day life, or it can be in your computer science, mathematics, anything, you have a number of solutions. So we need to pick whichever is the best for that scenario, right? So how do we classify these algorithms? So these can be basically classified into 4, okay, based on implementation, based on design, based on area of specialization and tractability. Now, when we say based on implementation, okay, so again, we can have 6 types. So when you have those set of codes which are recursive, okay, a function calls itself. So when you have those kind of code, you call it recursive algorithm. When you don't have it, you call it non-recursive, okay. When an algorithm gives you exact solution, you call it exact algorithm. Certain algorithms give you approximate solution, so they are approximation algorithm. And you have deterministic and non-deterministic algorithms, which probably you will be doing it in your 5th unit, right? So that is based on implementation. Then the second one is based on design. Design is you have various strategies how to solve these algorithms. So this a little bit of it I'll touch in this talk. So based on design, it can be brute force, which is most probably the trial and error method. Then you have divide and conquer, dividing a given problem into sub-problems and then solving it. Then you have greedy approach, right? You try to take every single step that you take is made of greedy choices. Then dynamic programming, which can be for solving optimization problem. And backtracking, which is you take few paths, and if it is not feasible, then you go back and then go for looking the other solutions. Then branch and bound, similarly finding out various feasible solutions and not going further when something is bounded based on constraints. Then you have randomization, approximation, and several such types of algorithms based on design. Then coming to area of specialization, you can have general algorithms or domain-specific algorithms. General algorithms can be based on sorting, searching, and finding mean, rank, median, those kind of general algorithms. And we have domain-specific algorithms, which can be string matching algorithms, graph-based, combination-based, and based on tractability, you can have easily solvable algorithms and unsolvable, intractable. So we have several such categories of algorithms, right? So when you have these many, you should know for your current problem, given that scenario, what kind of solution can be framed. So that is why you should know what are all available. And this is a broader area of research. So every single day we have a lot of such algorithms coming. These algorithms are all made for these existing problems. Now that we have several algorithms, how do you pick the right algorithm for the given scenario? So you have to consider, obviously we have several features to consider, and right now to bound this, okay, we'll consider only two important points. One is the time, the second one is space. So yeah, so you make an algorithm, see how much efficient it is in terms of time and space. So consider you are writing an algorithm for adding two numbers and it keeps running for 1 minute. You will be exhausted, right? So when the problem is smaller, obviously the time also should be smaller, time taken to execute that problem, right? Similarly, space. I do not know how you can imagine space, but you have been using these laptops, so you know what is ROM, RAM, right? So when you're writing a very small problem and it should accommodate in a lesser space, only then you call that algorithm as efficient. So these two points are, or these two features are very important when you're picking the algorithm, right? Next is rate of growth. So when we talk about time, an algorithm can run in constant time. An algorithm can run in terms of its input size. If I have 100 students, I'm processing the data of 100 students so as to calculate their rank, okay? And say if it is an university and we have thousands of students, based on the size, the time of that algorithm increases. The running time of that algorithm increases. So this is the rate of growth. Constant time, log of log n time, where n is the input size, right? Then this is log n, which is a bit bigger than this log of log n. And this is even bigger, okay, log squared n. Then this is n. N is the size of the input. So if it is thousands of students, so that's 1000 is n, right? So you should know that log square n is smaller than n. And each one is bigger than the previous one, right? So this is quadratic, cubic, and this is polynomial, exponential, and factorial. And these days we have lot of algorithms which are exponential time taking, and we are trying to reduce its time to polynomial time, right? That is a research area when it comes to algorithms. So now that you know a little bit of algorithm, let us see how to analyze an algorithm. So we have, these are 5 basic ways how you can analyze an algorithm, okay? So step count, operations count, asymptotic analysis, recurrence relations, amortized analysis. So first comes step count. Okay. So step count is where you have an algorithm. Okay. So what we are basically going to do is finding the time taken of an algorithm, so as to analyze if it is efficient or not. You can compare. So when I have a problem, I have n number of solutions. I compare each and every solution so as to pick the right algorithm which is efficient with respect to time and space. So when I talk about step count, I classify the statements into executable and non-executable statements, and I give a count of 0 to non-executable statements, and I give a count of 1 to all the executable statements, and find out what is the total count. Right? That is one way of analyzing an algorithm. Right? So here we have a sample algorithm. Okay, randomly we have some 3 assignment statements. Right? So every statement, see, begin and end both are non-executable statements, right? And these 3 are executable statements. Okay, so which is an assignment into A, this is an assignment into C, and assignment into D. Now we give a value of 1 to each executable statements, how many times they have occurred. So you multiply them. Okay, 1 into 1 is 1, 1 into 1 is 1, 1 into 1 is 1, which will be 3. So this is a constant time taking algorithm. So this is one way of how you can analyze how efficient an algorithm is. The second one is operation count based on the operation that is performed in that algorithm, right? So these operations can be categorized into 3. So the first one is sequence, where you have one sequence, then the other, and so on. Selection is based on a condition. You pick the statement P or Q. And the third one is repetition. M number of times or N number of times M operations are performed. Right? So this sequence statement, okay, it takes M plus N number of operations, which follows addition principle because it is just sequence. The second one is selection, which requires whichever statement you are selecting, so whatever is the time for that, so that will be the number of operations. Okay, if this P statement is selected based on this condition, okay, then P takes how much operation count, so that will be the answer, which is the operation count for this set of statements. So based on this condition, either P or Q, right? So maximum of whichever is the result, P or Q. Then the third one is repetition, which takes N number of times M operations. So it is multiplication, which follows the multiplication principle, right? So keeping these in mind, this is a very simple program. Again, begin and end. Within that, you have a swapping operation. So these are all basic operations, right? Assignment operation. You are assigning the value of A into temp, B into A into B. And every operation has its own cost. So we have randomly taken it as C1, C2, C3, right? And how many times it has occurred. So you can multiply the cost with its frequency and pay the total. Finally, you can sum it up. So whatever is the final cost, that is the time taken for that algorithm, right? And one more, where I've given a small looping, right? You have a for loop, and it runs from 1 to n. So between this 1 to n, you have this addition operation and then assignment operation, right? So you know that for loop comprises of 3 components. First is the assignment, then you have the comparison, and you have an increment or decrement operation, as you would have done in your C programming or C++, right? So you have 3 basic operations here. And generally, it takes some cost C1 to get this statement performed. And say for this statement getting performed, it takes a cost C2. Right? And this is just a termination statement for this for loop. So there is no cost involved for this. And how many number of times this particular statement is occurring is n plus 1 time, because it runs from 1 to n. And there is one more time where it comes and checks the condition and it turns false. So that is why it takes n plus 1 time. Okay, and this expression, it runs for n times because it is inside this loop which runs for 1 to n. And again, you multiply the frequency and cost and sum it up and find out the time taken. So far we have seen two types of ways how an algorithm can be analyzed, right? So this C is a machine dependent cost and this N is the input size, right? So the third important topic is asymptotic notation. So asymptotic notations are again one important way how an algorithm can be analyzed. So an asymptote is a line of curve in a graph that runs very closer to that curve, but it never intersects with that curve, right? So I'll show that in a figure. So before that, whenever we talk about this asymptotic notations, you should know what is the best case, worst case, and average case for any given algorithm, right? So basically, to understand that, I have taken a very simple example. So this is a given array, right? And what we are going to perform is a linear search. So linear search is one after another, right from the first till the last, we are going to hit every individual element so as to find if this X is present or not. So first case is the best case, right? Where, say for example, if this X is 20, so our hit will be in the very first comparison, right? So in the very first step, if we identify the required element, then that is the best case, right? So this is called omega. Okay, this is omega, and this represents the best case. And the worst case is when I want to find an element 45, but it is a linear search. So what we do is every individual element will be searched for, okay, and until we find that element. So here in this case, if X is 45, I'll be finding that element when I reach that very last entity, right? So that is the worst case. Average case is somewhere in between, right? So this is the case of a linear search with respect to best, worst, and average case. Now coming to big O notation, right? You consider a graph, okay? And yeah, before that, you know, when you draw a line is of the function which can be represented with y is equal to mx plus c. Similarly, every curve in here is a function, right? Now, this function is drawn between n is the size of the input, okay? You can consider the case of your institution where you have thousands of students, okay? When I feed into my algorithm, every individual input, okay? As the input increases, the time also increases. So this is called the rate of growth. Okay, this is the function t of n. For that input, what is my algorithm giving as the output? It can be the analysis of your marks. It can be the analysis of your extracurricular activities, anything based on the problem. And this c g of n, c is the constant, g of n is a function. Okay, this is an asymptote of this graph or this curve, right? It doesn't intersect, but it closely follows this graph t of n. Okay, why we are making this graph or curve to the actual curve is so as to find out what is the time complexity, or how do I relate my input or my solution with something closer to it. Not every algorithm gives you an exact solution. As I told you, we have several algorithms which only gives you some approximate solutions. right? Now, this big O notation gives you the worst case. Okay, big O notation puts the asymptotic upper bound. So if this is your curve, this is the upper bound. Okay. Now, if T of n, which is the actual curve for my input size is n, and for a time t, okay. Now, after a particular input, always there is a curve, asymptotic curve, which is above or greater than my T of n. Okay, which is if my T of n is less than or equal to some function into a constant, then I can say that T of n is the big O of G of n. Right, which means this T of n is less than G of n. Right, and this is the G of n, C into G of n is the upper bound of T of n. Coming to the second case, okay, which is big omega, which is the best case, right? So I have a curve T of n, and I have an asymptote of the curve, which is C into G of n, and always this C into G of n is lesser. So if T into C of n is always greater than C into G of n, then I can say that T of n is the big omega of G of n, which means T of n is greater than G of n. For some input, which is always greater than NO, which means before that it can be in any pattern. Right? Similarly, you have something called big theta, where this is my curve, okay, and there is one function G of n, which can take two constants. One is C1, the other one is C2. So with these two constants, I can have one upper bound and one lower bound. So these representations are, you have some function for your problem, okay. You can have asymptotes like this so as to approximate your solution. So this is one way of analyzing your algorithm, right? So far we have seen step count, operation count, then this is asymptotic notations. Then you have recurrence relations. So recurrence relations can be used for calculating time and space complexity, and any problem can be solved either using recursive or non-recursive algorithms. And these recurrence relations, they can be used to describe the running time of any recurrence algorithms. So when I say recurrence, you can consider that as an equation or an inequality. So you know what is equation, what is inequality, which can describe a function in terms of its value of its smaller input, right? And recurrence is required when an algorithm contains recursive call to itself, right? So there are several ways of solving recurrence equations. So you can have these substitution method, recurrence tree, then Master's theorem, we have difference method, polynomial reduction, then generating function. So there are several such methods. So these three are more popular. And I'll show you one recurrence relation. So this is a recurrence relation, and it indicates a divide and conquer strategy where you have n problem, n is the size of the problem, you divide it into half, right, and solve it. So this is a recurrence tree. So this n is the input size, okay, you divide it into half, and this sub problem is again divided into two halves, okay, and so on until you have the leaf nodes as one. The most simplest sub problem. Okay, so this is a representation of a recurrence tree, and again, when if we have to discuss this recurrence relation, it's a very elaborate topic. Just get to know that we have several methods on how to solve this recurrence relation. So these recurrence relations are relations how you can represent a solution to the problem. So if you can represent an algorithm in this recurrence relation form, then you can easily solve it using these methods, recurrence tree or master's theorem or substitution method, right? Now that we have seen how to solve or analyze an algorithm, right? We can see how what are the strategies that are available so as to solve the algorithms, right? So the prime important strategies that we can discuss for today is divide and conquer, where you are given with a given simple set of input. You divide that input into several subproblems, then you conquer the solution. Then you have greedy approach, where every single step you take will be towards achieving a local optimum that will obtain the global optimum. Then you have dynamic programming for solving optimization problems, backtracking. So you keep trying the feasible path. If something is bounded by the constraint, then you come back. Then branch and bound, where you look for all feasible solutions and you bound it by the constraints so as not to increase the time complexity in an unwanted situation. So what I've done is I have listed set of algorithms that comes under each and every strategy. Then I've tried to discuss one among them, right? So the first one is divide and conquer strategy. So as the name says, you have a problem. Okay, so from this you can see that the problem is everything is in lowercase, you are just capitalizing it, right? So what the problem is, one big unit, and you divide it recursively into subproblems. This is not just one step. You have recursive multiple steps, right? So you divide the problem, then you identify the solution for each and every subproblem, and then you finally merge it. That is how this divide and conquer works, right? So these are some problems, okay, for which the solutions or the algorithms are made using this divide and conquer strategy. So you have binary search, merge sort. So merge sort is you are given with a set of array, you divide it, recursively you divide it, and then you merge them together. Stassen's matrix multiplication is, you know that normal matrix multiplication takes n cube times to solve that algorithm, right? Where you have in your C programming, you would have done this, where you have 3 for loops, I, j, and k. So it takes n cube times, and Stassen's matrix multiplication, it aims to reduce that time, n cube time, right? And quicksort, where you take a pivot element from the given array. It can be the last element, first element, or a random element, and that element you try to put it in the correct place of that array. Then you pick the next element, and so on. Then you have finding minimum and maximum elements in an array, right? Then you have closest pair of points, where you have, say in a graph, you have some set of points, several points scattered, and you're trying to find out which 2 points is closer to each other. The distance among each and every point you will calculate. So how that can be achieved is, again, you divide the whole graph into 2 halves. Then each half is again split into 2 halves, okay, until you find 2 closest points. You merge them, merge the solution. Convex hull is again when you have several points. Okay, you try to identify the outermost points and you create a hull. Hull is a closed shape which is formed from joining all the outermost points in a plane. So I've taken this binary search here, right? So here you can see. So for first performing this binary search, you will have to have a sorted array, right? So when you have a sorted array, what you do is you divide the array into two. Okay, identify the midpoint. So when you know the midpoint, you take that value which you are searching, which is 37, and compare it with this midpoint. If it is greater, then you ignore all the elements in the front. Okay, you take only the second half. Now you have to pick this as the first element, this as the last element, and the middle element as the mid element. Now again you check this 37 with this value, and if it is smaller, you go front. If it is greater, you go back, ignoring all the other values. So you can see that in this scenario, this binary search, it takes only 3 steps for finding this value 37 in this array, right? But if it is sequential search or the linear search, it starts from the beginning till the end, or till you identify that element. You keep hitting every element. Okay. So in this case, it takes 11 steps. So binary search follows divide and conquer, dividing the given problem into, here you have 17 elements. So you are dividing the problem into halves, and which half to select. Based on that, you go and hit the element. So this is binary search. The second approach is greedy approach. So greedy approach, as I told you, you have to have every step that you take should be a local optimum. Okay, and that will guide you to attain the global optimum, right? In other words, optimum solution is obtained by creating greedy choices, right? So you have that is called the greedy property. So you have two properties which this greedy approach should satisfy. One is the greedy choice property, and the other one is the optimal substructure, which is when you have an optimal solution, it contains optimal subsolutions, right? And 3 things that you should keep in mind when you're following this greedy approaches: you should try for all the feasible solutions, then pick the local optimum choice. And once you take a step, you cannot go back, which is the third thing, which is unalterable. If it is alterable, then it is a backtracking approach, right? So these are some problems which are solved using greedy approach, right? So Huffman coding is when you are transferring data from your place to your friend's place. Okay, see the codes or the value, the data is transferred in the form of codes, usually in the form of ASCII codes. So how do we optimize this code? How do you reduce the size of the code so as to reduce the size of your or increase the efficiency, right? Space and time efficiency. So addressing that is Huffman coding. Then you have fractional knapsack. So knapsack is a bag. Okay, so where you have some set of elements in front of you, you want to take enough number of items so that your profit is better when you're placing the maximum number of items into your knapsack. And fractional says that the items can be divided. So if I have 5 kgs of apple, I can take 2 kg, 1 kg or so. That is fractional knapsack. Tree traversal, this is pre-order, in-order and post-order, right? How to traverse a tree. So all these problems can be solved using greedy approach. So in this session, we will be discussing Kruskal's minimum spanning tree. So before we discuss that, let us discuss this spanning tree. So this is an undirected graph. Okay. So G stands for graph, and these are vertices, and these lines are the edges. Right. So a spanning tree is one which can have lesser number of edges, no issues, but every vertex should be included. Okay, so here we have 4 of the spanning trees for this given graph. So you can see that all the vertices are present in all these 4 graphs, but you can have minimum number of edges. So these are called spanning trees for this undirected graph. So the second term is minimum spanning tree. When you have weights to all these edges, we have to create a spanning tree such that the cost is minimum. We pick only minimum cost edges, right? So you have to follow a procedure with which you can create such a minimum spanning tree, right? So this is one minimum spanning tree for this given undirected graph. Okay, so which includes 4 plus 1 plus 2. Now, having these in mind, I'll discuss this Kruskal's algorithm, right? So Kruskal's algorithm, you just watch this image. So Kruskal's algorithm, it adds edges to the spanning tree one by one, right? And as I told you, it follows a greedy approach because at each step, it adds least weight edges to the tree, right? So the steps for how this Kruskal's algorithm works is, first of all, the given edges, right? So based on the weight, the edges are sorted. That is the first step. Okay, it is first sorted. Then you keep picking each and every smallest edge to your tree. And once it forms a cycle like this, then you ignore that edge. And you keep repeating this procedure until you have V minus 1 edge to your tree. So V is the number of vertices. Here you have 5 vertices, A, B, C, D, E. So until you have 5 minus 1 edge to this, then you can complete that minimum spanning tree. So here you have that tree. So you can see that you are considering 1, 2, 3, 4, and so on. Minimum, starting from the minimum weight, you keep adding each and every edge to the tree. Right? Once it forms a cycle, okay, this cycle, you are just ignoring this edge. That is Kruskal's algorithm. This follows a greedy approach. Why we say greedy approach is at each and every step, we are going to pick the least weight edge. Right? Then you have the next strategy, which is dynamic programming. So dynamic programming, it usually is used for solving optimization problem. Right? Optimization problem is in terms of profit, you can say I need maximum profit, or in terms of cost, I can say I need minimum cost. Then you go for this dynamic programming. Okay, optimization problem. Now, if you consider this divide and conquer, in divide and conquer, we partition the problem into disjoint subproblems and solve it recursively and combine the solution. But in case of this dynamic programming, where we use it is when all the subproblems are independent, are not independent. Okay, which is when they are dependent. One subproblem is dependent on the other. Right, which is when they share the same subproblems, right? So in that case, what we do is we solve the subproblem and we store it in a table so that we can retrieve the necessary data when required. We don't have to compute it again. Okay, and what we do is we can always retrieve data when we need it, but again, we can also plot it in the form of a state space graph so that you know where to bound it. Based on the constraints, you can bound it, and you don't have to proceed forward, so that you can reduce the time taken for solving that problem. Right. In coming to the characteristics of dynamic programming, again, it has two important characteristics. One is the optimal substructure, where I've already told you that you have an optimal solution, then it means that it contains optimal sub-solutions, right? And the second characteristics is it always has overlapping sub-problems, right? So keeping that in mind, again, I've taken 4 popular problems which are usually solved using dynamic programming. So 0-1 knapsack is where you have a knapsack or a bag and you have n number of objects in front of you which are not divisible, right? So in that case, you want to put maximum profit item into the knapsack as a whole. Either you take that item or you don't take it. That is 0-1 knapsack. Then you have matrix chain multiplication, which I'll discuss now. Then you have longest common subsequence, where you are given with a string and a pattern. You want to find out what is more common in both these strings. That is longest common subsequence. Then you have optimal binary search tree, which means you have a binary search tree. You want to place a binary search tree in such a way that it gives you optimal search terms, which is it. You can solve it in a easier or time efficient manner. Say you have 3 nodes, 1, 2, 3. You can place 1 at the bottom, 2 in the root node, and 3 in the bottom, because 1 is smaller and 3 is greater, right? Or you can have 3 as the root node and then 2 and then 1. So similarly, it can be placed in n factorial ways. So in which way should I place it such that it gives me optimal solution, which is for searching? That is optimal binary search tree, right? And here I have discussed matrix chain multiplication. So, matrix multiplication requires that the first matrices column should be equal to the second matrices row. Only then you can do this matrix multiplication. Now, given that you have 4 matrices in sequence, okay, which 2 matrices should I multiply first? Is it this one and this one first? Or should I multiply this one first? So in which sequence should I multiply so that it gives me lesser scalar multiplications? Okay. So keeping that in mind, we have several such algorithms which can be solved using dynamic programming. So as to reduce the time complexity, right? This is matrix chain multiplication. So I'm just discussing the problems. Obviously, if I have to discuss the solutions for all of these, it will at least take 30 minutes, minimum 30 minutes to solve one such algorithm, right? And finally, coming to backtracking approach. So backtracking and branch and bound, both are a little similar in the way that both of them use state space tree, and both of them use bounding conditions. The most important difference between backtracking, branch and bound is backtracking follows depth first search and branch and bound uses breadth first search, right? So you can see this image where you can understand what is backtracking. It follows a particular path, okay? It follows a particular feasible path, but when it finds out that it is not feasible, then it goes one step back and finds out what are the other options. So with this approach, you have 3 significant problems, n-Queen's problem, sum of subsets. Then you have Hamiltonian circuit, also called as Hamiltonian cycle. So yeah, so this usually uses brute force approach to try all possibilities, and it finally freezes the desired solution. And usually we don't use backtracking approach for optimization problem. Right? So in here I am discussing this n-Queen's problem. So this n-Queen's problem, you know that you have a n cross n chessboard, and you have to place n number of queens in this chessboard. So in this case, you have a 4 cross 4 chessboard, and you have to place 4 queens. And it should follow that the queens cannot come in the same column, it cannot come in the same row or in the same diagonal, right? So first you place a queen, right? Then you check what are the other possibilities for placing the second queen. So it can be placed here. Now that when you're trying to place the third queen, you can't have any such option. Then what you do, you go back. So for that only we have this state space tree, right? So the first queen is placed, okay, and then in the second step you're trying to place the second queen. So after you place the second queen, it is mandatory that in every row you should have one queen at least. So in this case, you can see that you cannot place the third queen here, you cannot place it here because this will hit. Here also you cannot place it, here also you cannot place it. So this is not a feasible solution, right? So you go back, check what are the other feasibilities. If I cannot place in the third place, then can I place it in the fourth place? Yes. If I can place it in the fourth place, then go to the next step. Can I place the third queen here? No. I can place it here, right? Fine. So next, you can go to the next step where I'm placing the fourth queen. Now you see, I cannot place it here. No. Here also I cannot place it because this will hit. Here also I cannot place it. So this is not a feasible solution. So again, go back. Now you don't have any other options. Again, you go back. Don't have another option, so you can go back. So this is backtracking. So this is one feasible solution where I have placed the first queen in the second position in the first row. And in the fourth place, I've placed the second queen. In the first place, I've placed the third queen. And the fourth queen is placed in the third position. So this is one feasible solution. And this is another feasible solution, which is the mirror image of this itself. Right? So this is the 4 queens problem. So the strategy is backtracking. Once you cannot go any further, you go back and try out what are the feasible solutions. Again, you don't find a feasible solution, you go back, and so on. So try out all the feasible solution and freeze the desired solution. Right? So here is an 8 queens problem. So once a queen is not able to be placed, then you go back one step at a time. Right, so this is how we can place a 8 queen in a 8 cross 8 chessboard. So then coming to the last strategy, which is branch and bound. Again, it is very, very similar to backtracking. Here, the most significant point is you bound at a particular point based on the constraint. So this is an example of a state space tree. So this is a very common example where you have 2 boys and a girl, and the condition is the girl should never come in between when they are sitting in a bench, right? So when you have 3 students, you can have 6 possibilities, okay, 3 factorial base. So here you can see that this is one place okay, where the girl is sitting in the middle, and this is one place where the girl is sitting in the middle. So boy 1 and boy 2, boy 2 and boy 1. So this can be plotted in the form of a state space tree, right? So as I told you, this branch and bound, it follows breadth first search, which is you start, okay? In the first place, I can place the boy, first boy. In the first place, I can place the second boy or the girl, right? So this is breadth first. So next, what is the possibility? If I place the boy first, then I have two options. I can place the second boy or the girl, right? Now, according to my constraint, I cannot put the girl in the middle. So this is a bounded condition. I cannot go any further. Even if I have several possibilities, this is not what is required. So I'm bounding this. Okay, now, if I place the second boy first, then I have two options. The first boy, then the girl. Okay, in the second place. So we have two options. Again, if the girl is coming in the middle, this condition is bounded. That is why you call it branch and bound. Already I have put the girl first. Now I have two options, boy 1 and boy 2. Then again you go in for checking what is the next possibility. So I've already placed the boy 1, boy 2. What is the other case? So I can put the girl. So this is one feasible solution. This is already bounded. Next, I go for the other scenario where I have the boy 2. Okay. Now I already have the boy 1. What is the other option? I can have the girl. So this is a feasible solution, right? This is already a bounded case where I cannot have the girl in the middle. So I can go for the third scenario where I have put the girl first, right? And I have placed the boy, first boy or the second boy, and I can have the other person left. So these are also other feasible solutions, right? So here again we have several problems, and the most common problem which are solved using branch and bound is 0-1 knapsack. Then you have traveling salesman problem or Floyd-Warshall algorithm, right? So here I've taken traveling salesman problem, where this person, he starts from one place, right? And he should reach all the locations given in the graph, right? And he should again come back to the original starting point. Now, usually why we go for this branch and bound is for solving minimization optimization problem, right? So even though you have several options of how this person can reach the various other destinations and then come back to the original source point, now by using this branch and bound approach, you can find a more optimal minimization problem, so that he takes minimum cost in traveling, right? So that is another example of branch and bound. So that is the end of all the various strategies. So in this given little amount of time, so what I've tried to do is I try to bring out what is the need of this design and analysis of algorithms. Then how do we do it, and what are the other various strategies available for solving these kind of algorithms. So the main thing is, any problem you have, okay, you say this traveling salesman problem, this is also a problem, right? Or you need to stack something, or you need to sorting, you need to search something. So anything, any basic or advanced problem you have, it can be solved in different ways, but we need to pick an optimal solution, right? And obviously optimal solution is based on scenario. It's not always minimum cost solution. It is not always maximum profit solution. It is based on the scenario, based on the features that you have, or the whatever options you have with you for this scenario, you try to solve. So for that, we have several strategies, right? And this is a good research field. From your second year itself, you can start exploring what are the feasible or what do you call it? You can explore the research areas, and every time you think of an algorithm, you think of the multiple ways how you can solve these problems, and then try to pick the most optimal solution. So design and analysis of algorithm is a very significant subject in computer science engineers life. And yeah, obviously it is also helpful in your placement preparation. You just go ahead with a better preparation so as to get settled in a very good company. Right? Yeah. So thank you. Yes, I believe I'm audible. Yeah. Thank you.
Sahana?
Yes, ma'am. Yes, ma'am. Thank you, ma'am. First of all, a deep sense of gratitude to you, ma'am. I'm sure all of us would have gained greater insights and would have become even more familiar with our subject design and analysis of algorithms. So, on behalf of all the participants and honorable patrons and conveners, I would like to sincerely thank you for taking some of your time and giving us this amazing session, ma'am. Thank you, ma'am, and thank you all.
Thank you for giving me an opportunity here, and special thanks to Shanmugapriya ma'am and Mr. Danu sir for having me here, for giving an opportunity to discuss with a different set of people. Yeah, thank you. Thanks a lot.
Thank you, ma'am. Sindhu ma'am.
Thank you, ma'am.
Students, I have sent the feedback form in our class group, ma. Just fill that one. Okay, thank you, students.
Okay, ma'am. Thank you, ma'am.